Hello and welcome to my presentation on the curvature of the Earth. I'm going to look at debunking the so-called 8 inches per mile squared calculations. We're going to use established numerical values to calculate the precise values of the Earth's curvature. We're going to do trigonometric and algebraic calculations. I'm going to use spreadsheets to calculate values over the boundary values. I'm going to compare and contrast these values. Going online, you find the Earth curvature calculator, which gives you an alleged calculation of the curvature you're supposed to see. So from the distance of 1 mile to 1,000 miles, you have a curvature of 0.0013 miles, 0.67 feet, and all the way up to 1,000 miles. I've done the same calculation here on a spreadsheet. I've done the Earth radius in terms of miles of 3,957. Angle subtended, curvature length times, etc. 8 inches per mile squared. And I'm going to compare from an initial comparison. We have that's the same as that value, that's the same as that value, and all these values are for 1 to 1,000, and these are 1 to 1,000, and you'll see there's quite a discrepancy here just from using the initial value here. We've got 125.632 miles, 126. 66,000 again here, but all the sixes. So there's quite a range of variation there, immediately obvious. Look at the term of 8 inches per mile squared. Now I've got my physics head on and go units, units, units. What do you mean by that? So per means divide. So 8 inches per mile squared, like percent, 25% divided by 100, 0.25. So in that terminology, 8 inches per mile squared would be 8 inches divided by a mile squared. In terms of that, so you have a length divided by the square of a length, which is 1 over length, which is not a length. So how can that be a length? If I substitute those values in and do those calculations, I've got 8 inches per mile squared and divide by the mile squared here. That's what I get the values here. And then it's really obvious on a curve. So the further you go away from a point, you end up getting this real sharp curve coming down, and it's an exponentially decaying curve. So it would end up being a initial curvature of being such and such of 8, and then dropping down. So it would be a very weird sight indeed. What about not going to divide then? What about timesing, multiplying? More mathematical. 8 inches times mile squared. So do that again dimensionally, it ends up being L cubed, which are the units of volume. So that can't be a length, therefore that is incorrect. We're not getting very far here, are we? So let's start off by going to Wikipedia, and the Earth is theorized to be a spheroid, which is oblate spheroid actually. So the radius ranges between a maximum of 6,378 kilometers to a minimum of 6,357 kilometers. So the range is in miles. So we're going to take these two radii, get the average, got the average now, calculate the circumference, and you end up with 4.00 times 10 to the 7. I've included a large precision here because we need these values in there as we calculate. Do the same with the miles, these ranges, and just get the average. Pretty straightforward so far. The circumference, given that in meters, we're going to have the meter has the angle of 360 degrees in a circle, divide by that, and you end up with, as you would expect, a meter to have an incredibly small angle, 10 to the minus 6. Again, if I'm going to convert now from meters into miles, then I multiply by that, and again 1 mile has a small number, but obviously bigger than that one. If we use trigonometry, now we have a simple triangle here. The radius here, the angle is A, the radius is R, and the radius R there. If I then have a point here on the Earth, and I go to a point here, a distance D, I've dropped a height here, H. So the H here, simple trigonometry, draw it across, have a right angle triangle. So that distance being the radius, the whole distance, then R minus H is that distance here. I have a right angle triangle. The cos of the angle, cos of A, is adjacent over hypotenuse. So you have r minus h over r. So it's r minus h divided by r, because that length is r. Multiply it out, and they end up with r cos a equals r minus h. Rearrange, h equals r minus r cos a. H equals r, take it out of the bracket, 1 minus cos a. Dimensional analysis, happy days. Length equals length, correct units. There we go. That's a good start. We need to talk about the cosine function. The cosine function has, at the value of 0 degrees, it has a maximum value of 1, and it has a minimum value of minus 1 at pi, which is 3.14, so that's 3 on the x-axis here, courtesy of wxMaxima. So that is a minimum value of minus 1 at pi, which is 180 degrees, and then it goes back up to a maximum value of 1 at 2 pi, 360 degrees, which is 1 plus 1. So you've got the range that goes from 1 to minus 1 back to 1. It has values of 0 at pi by 2 and 3 pi by 2. Or in old currency, 90 degrees, 180, 270, 360. So here we have like my version of the Earth. We have the radius a, the height h. The yellow guy here is going to stay on the top, and then the green guy is going to progressively move around the Earth. At the moment, there is no angle between them. He's on top of each other, but there's no height. He hasn't gone round yet. So we take that equation, r 1 minus cos a. This angle A is 0 degrees. Remember, the value of 0 of cos is a 1. So you have 1 minus cos of 0, which is 1 minus 1. Of course, obviously, there is no curvature. Now we're going to shift to an angle here, A, of 30 degrees. Taking that same equation, 1 minus cos of 30. Cos of 30 is root 3 over 2, which is 0.866, which is that one. I'm trying to get it up to the value there, 0.86, and then we have that height value dropped is 10 to the 5 meters. Then looking at the snapshot here of a spreadsheet calculations, the height here is 8.5305 calculated using a spreadsheet calculations. I've got it rounded up, but you see that is pretty good. So that's giving authenticity to it. Then I've compared that with a calculation given 8 inches times mile squared. The value here is 530, and the theorized value is already a difference of 12 miles. Now we're going to take an angle of 45 degrees, so cos of 45 is 0.7071, which is that to there, and minus 1 root 2 over 2, and we have now a value of 10 to the 6 meters. Calculated value here, and there is the spreadsheet value, so the values are the same. Happy days, all clicks in. And then we now see that converting to miles, we've got quite a difference now of 60.01 miles for the 8 inches times a mile squared. Now we can take 60 degrees, and the cosine value of 60 is a half. So 60 degrees, 0.5 is about there. It's all approximate because of course we've got the scale here is in decimal. And then we end up value increasing of 10 to the 6 meters. Calculated value here, 3.1838 times 10 to the 6. Again, pretty bang on for the actual spreadsheet values. Converting it into miles, we've got quite a massive discrepancy now of 189 miles from the 8 inches per mile squared. Now we're going to go for 90 degrees. Remember, the cos of 90 is 0, so that's 0. And it's really obvious because that to there is that height there, which is the radius. So then we have the straightforward radius of the Earth. And then that matches very nicely with the calculated version and also the spreadsheet version. And then we see here with the converting into miles, there is a increasingly bigger discrepancy with the 8 inches per mile squared calculated value, 920 now. Then if we go full on to 180 degrees, so we've now got all the way down here, so it's clearly a double R. So you've got 2R. 180, what's the cosine of 180? Well, it is 3.141, there we go, minus 1. So 1 minus minus 1 is 2R, happy days. Double the radius, obviously, 10 to 7 meters. And then we check that with that calculated version with the spreadsheet version sorts, fits in. Then we see that the conversion into miles does not match that substantially. It is substantially out. The 8 inches per mile squared is over double. It's nearly 12,000 miles difference between the two. So it's clearly falling down. If we now go 270 degrees, and it's because a cosine is a repeating function, it's now 270, which, as I said before, is a value of 0. Same as 90 degrees. Then we just have, obviously, that height is the same as the radius, the curvature. So we end up with the same value. Checking that, spreadsheet's working well. Converting into miles, of course there's quite a difference here because as before at 90 degrees same value, it's about the same difference of 920. Then we put them all together, we look at the spreadsheet for the 8 inches per mile squared, and it just goes absolutely off the charts because I've gone through that and checked, gone like 30 degrees, 45, 60, 90, 180, 270. And then you just see as you start increasing values in feet, it becomes, and miles becomes insane. And then you get to, well, I've highlighted here in red because the circumference of the Earth and the radius, I mean, these values are way in excess of the Earth's circumference. It cannot be true at all. Reference our Wikipedia for the values of the Earth radius, the Earth curvature calculations right at the beginning. There's a website. And for using Maxima, which is a really helpful software tool for doing mathematical calculations. I used it a lot during my teaching with the OU, and it's really helpful for doing solving equations and doing graphical plots as well. So, and it's, as far as I know, it's still free. So that's the conclusion. I've done that, so you'll see that the 8 inches per mile square calculation is only true, if you go right back to the beginning, is only true for very small values. It's only similar to what I've calculated here. I'm not saying it's true, but I'm saying it's only similar to small values. The minute you get into large values, it falls down, whereas the correct calculation is using the cosine dependency. Thank you for watching. I hope that's useful, and any comments, likes, whatever in the box, please. Thank you.